Okay, and we're back. Okay, so this is part 2 of our time trial of paper 2. So, I'm sorry I overestimated myself. I thought I can finish before the end of school, but I couldn't. Okay, so A5 is here. A piece of magnesium ribbon was placed in 100 cm cube of da 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 da. Then measure against time at room temperature and pressure. Result below. Okay, I don't know why, but there's some problem with my diagram. So I just drew it again for you to see. Time. Let's see, when did it start to plateau off? It started to plateau off at around 40. I draw at the I draw at the wrong screen. Okay, around 40 seconds, it started to plateau. Oh, okay, sorry, 50, 50. Explain why the reaction stopped after 50 seconds. So what do you think could have been the reason? Is actually that they didn't say what is in excess and what is not, so you can just say that the reactants was used up. Okay, it is known that adding small amounts of copper can help to catalyze the reaction. Explain in terms of particle theory how the catalyst changes the initial rate of reaction. Now this is actually from your notes, so I will not go through. C. I repeat the experiment 3 times with a different condition or reagent from the original experiment. The 3 experiments are as follow. So this time, I'm adding some powdered copper to the acid before I add my magnesium ribbon. So it's already stated here that small amount of copper is a catalyst. So what this is that there's a presence of the catalyst. Okay, secondly, I'm adding dilute sulfuric acid, okay, instead of nitric acid. Now, sulfuric acid versus nitric acid, is there a difference? And is there a difference in their concentration? Let's see. First, this is 100 cm cube of 0.5 mole per dm cube of dilute nitric acid. Now, what is the concentration of H plus here? It is also 0. I wanted to ask the concentration. So the concentration is 0.500 molar. Okay, what's the number of moles of H plus? It will be 100 over 1000 times 0.5. That will give us a 0.05 mole. Right. Okay, let's calculate the number of moles of hydrogen ions as well as the concentration of hydrogen ions over here. Okay, so this is the concentration of H2SO4, 0.25. Now, what's the concentration of H plus? It should be twice the concentration of H2SO4, because for every 1 mole of H2SO4, it will become 2 moles of H plus and 1 mole of why? I'm too tired. SO4 2 minus. Okay, so it is 0.5 mole. Okay, then it's 100 cm cube of it. So the number of moles of H plus is again 100 over 1000 times 0.5, which gives us 0.05 moles. Okay, so you see that, let me change the color here. See that here the concentration is the same, the number of moles is the same as over here. So there's actually no change in concentration, no change in number of moles. So here I will write no change. Here is catalyst. Lastly, I add some aqueous copper 2 nitrate. Now they didn't add copper, the metal, as a catalyst. They added copper 2 nitrate. When you add copper 2 solution to magnesium, what will happen? Okay, the correct answer is this is more reactive than copper 2 plus, a displacement reaction will occur. Okay, so Mg plus Cu2 plus gives us Mg2 plus Cu. So what happens here is that it uses up your magnesium to become Mg2 plus. Okay, now they didn't tell you what is limiting. So strange. Okay, then you assume lah. Let's assume that magnesium is the one that's limiting. Okay, in exam you can ask the teacher if you like, not sure. Okay, if the teacher think they cannot tell you, they'll just say I cannot tell you. But if it's a valid question, the teacher will tell you that okay, let me check with my colleague. Okay, so for experiment 2, there's catalyst, so obviously the rate of reaction must be faster, but there's no change to the number of moles or anything, so it should plateau off at the same place. As in, it should plateau off at the same 480. Okay? Experiment 3, there should be exactly no change. Exactly the same graph because the number of moles of acid and everything is the same. So 3. Lastly, we actually use up more magnesium. So, not only should it be slower, it should end off like at a different level. Okay, so this will be 4. Because let's assume that magnesium is limiting, then there will be less hydrogen gas involved. Question 6. Students carry out the following steps to prepare hydrated salt. Okay, so they want pure, they want it dry, and they want it to be hydrated. Acid plus excess insoluble carbonate. So first, you measure the acid, pour into a beaker, you add excess the carbonate to the acid until it no longer dissolve. Okay, so it means that it is saturated. Here, then they heat it for a while and filter to collect the residue. Identify 2 mistakes in the procedures to prepare the hydrated salt. So in order for you to do this question, you yourself must know what are the steps to prepare a hydrated salt. Okay, if it's a hydrated salt, it means that say no to evaporation to dryness. We can only use crystallization. Okay, we can only use crystallization. So how can we do crystallization? First, so these 2 steps is okay, because we want to have a saturated solution before crystallization can occur. So for crystallization to occur, step 3 is wrong because we should not heat it. Instead, we should let the solution cool down to form crystals. Okay, so 1, the mixture should not be heated in 3, but should be cooled for crystals to form. Now the second thing is they want dry crystals. For evaporation to dryness, it's very easy to obtain a dry sample because just heat and heat and heat and heat until you're sure all the water is gone. Okay, but here when it's crystallization, we always need to wash it with cold water and then dab it dry, or we use a lamp. Okay, so we wash with cold distilled water and dab dry at the end. Suggest a possible identity for the salt prepared. Okay, you don't know a lot of hydrated salts, so one of the few that you know should be the copper 2 sulfate with water. State the respective acid and carbonate that should be used to prepare your suggested salt in A part 2. Okay, if it's a copper 2 sulfate, what is the carbonate we must use? It must be copper carbonate plus the acid must contain the anion, so H2SO4. Anything else? Let me see. My mouth is tired. Okay. Next, another student want to prepare pure calcium sulfate salt. So are the procedures suitable for the preparation of pure dry calcium sulfate? Explain your answer. Now, whenever we talk about salt prep, the first question we should ask ourselves is it soluble or insoluble salt? So let's ask ourselves, is calcium sulfate soluble or insoluble? Okay, answer is it is insoluble. If it's insoluble, the method is clear. There's only one way, which is ionic precipitation. Okay, so therefore, these steps are not suitable at all because this is not for ionic precipitation. Okay, explain your answer. So you say no. CaSO4 is an insoluble salt. Okay, if I react, if we react CaCO3 with H2SO4 an insoluble layer of CaSO4 will form around CaCO3 and the reaction would stop impure salt as the reaction did not go to completion. Okay, so write a balanced chemical equation with state symbol for a suitable reaction that can be used in the preparation of calcium sulfate. So to prepare calcium sulfate, ionic precipitation. To do ionic precipitation, I must start with two aqueous solutions. Okay, I must have solution A and solution B to give me C. This is a solid and another solution. So I can filter this out. Okay, these two must be, of course, aqueous as well. One containing the cation, one containing the anion. So let's just choose any example. Any calcium salt that's soluble. Okay, usually I use nitrate lah. Let's just use nitrate because all nitrate salts are soluble. Plus, let's say anion. Anion must be a sulfate. Let's say potassium sulfate. That will give us calcium sulfate. Calcium sulfate plus potassium nitrate. Okay, this is the complicated question that I also don't want to read. Okay, so first, let's just slowly read this. Okay, ozone is a triatomic form of oxygen. Dang, they draw for you already. Based on the dot and cross diagram, how can I draw the number of bonds? Okay, 不要想这样多先。It's a pale blue gas, low concentration. Okay, this part per million for this compared to oxygen. Okay, it's air pollutant, damage the respiratory system. To have ozone in stratosphere is good though. Okay, why? It acts as a primary UV radiation shield. Okay. Okay, it is formed as part of natural cycle similar to nitrogen and carbon cycle. First is the decomposition of oxygen molecule into two atoms. Okay, maybe you want to write it down first. Oxygen in the presence of UV becomes two oxygen atoms. Each can combine with another oxygen atom to form ozone molecule. The rate of reaction of 2 is faster where the pressure is higher. Okay, so here's the diagram. So this is reaction 1, where the molecules split into 2 atoms. Okay, each atom can combine with another oxygen molecule to form fast. Okay, so this is the second reaction. Reaction 2 is faster when pressure is higher. Faster when P higher. Reaction 1, what did you say? Higher, my spelling is atrocious. Higher than faster. Faster when P increase. Then ozone molecule form absorb UV and split to form an oxygen atom, an oxygen molecule which produce a lot of heat. Two and 3 rapidly interconverts oxygen atoms and ozone. Okay, so this is 4. What are they asking? 我自己都有点乱。Indicates an atom or molecule from one reaction goes on to take part in another reaction. Okay. So this atom goes on to meet them. Okay. Then it will fast become these 3. These 3. So this coming back here, this is 3. For every time they do this, I get 90 kilojoules of. So this is 2, that's 3. It was so confusing. Okay. This is 2, that's 3. Okay, 4 is here. 1, 2, 3, 4. Okay. Still not done analyzing yet. Okay. Chlorofluorocarbons, CFCs, destroy the ozone. Okay. Oh my god. Okay. Okay. CFC13. CFC113. Inert, synthetic. There. Some data about bond strength. Okay, can. Okay, that one later then we use. Calculate the volume of ozone present in air. The air contains 156 tons of oxygen. Okay. So, first off, you need to find what's the volume given the mass. Now, how do we convert tons to grams? Tons is 10 to the power of 6 grams. So, the volume of oxygen, first we can find the mass, convert it into grams, divide it by oxygen gas, the molar mass is 32 times 24 dm cubed. I'll end up with 117 times 10 to the power of 6 dm cubed. That's the volume of oxygen gas. Now this is actually, it's written here, oxygen gas is 21%. Okay, so let's convert your ozone percentage of O3. It is, I wrote down the formula in your classroom, 0.375. Okay, so 0.375 divided by 10 to the power 6 times 100%. That gives us a very small percentage. Okay, let me just write it in the SF. 1, 2, 3, 4, 5. Okay, so to find out the volume of ozone, just take 117 times 10 to the power 6 divided by 21 times 33.75 times 10 to the power minus 5. 209 dm cube. Okay, pause for a while. You can take down the answer, and I'm going to erase because there's no space. Okay, erase this. Dun 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 dun. Okay, I'll just keep the answer. Okay. Next, at which altitude is the rate of ozone formation the maximum? Okay. Going back to ozone formation, you want it to form this as fast as possible when pressure is higher. Let's look at when pressure is the highest. Okay, actually you don't need to look at when pressure is the highest, you just look at the graph. This is the ozone amount. So this is when ozone is highest. It is around 23 km. Suggests why stratosphere is a warmer layer than the top of troposphere. Okay, because here, right, you see that for every mole of ozone that spits out over here at the stratosphere, we see that more ozone are being present. So it is hotter because for every mole of ozone spitting out, it gives off this is delta H equals to negative 90 kilojoules per mole. Okay, so it keeps giving off heat. This reaction keeps occurring and keeps giving off the heat. Okay, so the higher the altitude, the faster the reaction because the greater the concentration, and therefore the stratosphere is warmer. D. Which two reactions, when taken together, are equivalent to reaction 4, which destroys the ozone? Okay, so you want to destroy the ozone. Here, there's the ozone here, plus oxygen gas. Dun, 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 dun. Okay, so it's actually this reaction plus this reaction. You'll see that I can cancel out this, cancel out this, cancel out this, cancel out this. So it's actually O3 plus O gives us 2O2. Okay, so O3 plus O gives us 2O2. So it's 6 and 7. Okay, next, E part 1. Energy of UV light is equivalent to 400 kJ per mole. Suggest why is it decomposed by UV light to form chlorine atoms rather than fluorine atoms. Then you go back to this chart again. Now, it can either break off a CCl bond or a CF bond. Let's look at the bond strength. Okay, a CCl bond, this is how strong it is. A CF bond, this is how strong it is. So, UV light is 400 kilojoules per mole, has sufficient energy to overcome this, but not to overcome this. Suggests a further bond change we expect to occur in CFC 13 molecule. Okay, what else can occur? Note that your CC bond is also less than 400. Okay, so it could also break your CC bond. 3. CFCs have now been replaced by other compounds from the list, most likely to replace CFCs. Okay, you want it to not have CCl bonds. right? Because CCl bonds break more easily. Okay, so if you look at everything, right, there's only one without CCl, which is this. So that you just choose that. Okay, F part 1. What is the enthalpy value? What's the value of for enthalpy change of the reaction here? Okay, now how can you do this question? Okay, every time ozone splits, it gives out 90 kilojoules of energy. Okay, so every time ozone is formed, it should take in twice that amount of, okay, so let me just write down ozone every time it splits into O plus O2, okay, this delta H equals to negative 90. Okay, so now it's the opposite. I times 2 the whole thing. Okay, 2 oxygen atom is equivalent to 1 oxygen gas. So let me just write it as 3. So this one, obviously, my value must times 2 here to become negative 180. Okay, but they're asking me from the opposite direction. Okay, so what they want is 3O2 gives me 2O3. Therefore, my sign must change into positive 180 kilojoules per mole. Okay, hence, you need to draw an energy profile diagram for this reaction. So, how can you draw this? Let me draw it for you. Energy here. Now, it's a positive delta enthalpy change. If it's a positive change, your reactants must be at the bottom, your products at the top. Energy profile diagram. Oh, okay. When it comes to energy profile diagram, it means you must draw the hump. Okay, so here is your 3O2, here is your 2O3. From here to here, where's the delta H? It is actually like this. Delta H equals to positive 180 kilojoules per mole. Okay, did they ask you to draw the activation energy? Okay, whenever you draw an energy profile diagram, just label the EA. Okay, the appropriate data is this part. So you must be able to label the correct value here, 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 okay, and obviously your reactant must be below your product. Yeah, so this last question is not say very easy. It needs you to read a lot and interpret a lot of data. Okay, so you need to be patient, slowly read it through, okay, and just write down your notes as you read. That's what I always do. I write down my notes as I read so that when I look back, it's faster for me to find out what information I require. Okay, so that's all. Thank you.